everyone, good evening. I'm Fariha Harun from Tallinn University of Technology. Together with my supervisors, I have developed a study called Heating Demand as the Indicator of Renovation Depth in Soviet-era apartment buildings. So, why does it matter? So, buildings are responsible for 40% of energy consumption and 36% of carbon emission in European Union. And in case of Estonia, we have more than 50% of buildings which are Soviet apartment buildings. So these buildings are basically this industrialized standard design building which was generated, which was built to handle the housing crisis after Second World War. So the problem here is that these buildings in the building registry or national building registries, the buildings are kind of like this building archetype, which is the first building, but in reality, these buildings has been through different type of renovation, increment, and the renovation process is very incremental and uneven over the decades. For example, some has partial insulation, some has new windows, some has HVAC reconstruction as well as deep renovation. So this caused a biggest problem when we have the UBEM calculation, because UBEM is heavily relying on static archetype, but the renovation history is causing a miscalculation in energy estimation. So to handle this problem, we are considering to move from static archetype to a dynamic archetype. So what is dynamic archetype? Dynamic archetype is condition-aware, dynamically updated building condition model. So this study is the first step of developing the dynamic archetype frameworks. So that leads us to the research question. Can heating demand be used to classify the renovation depth in Soviet-era apartment buildings? To achieve or answer these questions, we have followed basically few steps. So we have simulated 8 envelope scenarios for renovation situation for 44 buildings in Estonia. And we have classified the results in 4 energy demand tier. And we have also validated the results against subtype analysis and we also use some optimistic U value to understand the model's validation. And overall, combining this, we have developed a mock-up for the first step of dynamic architecture. So for this study, we have used a neighborhood in Estonia, in Mustamäe district, and there we have used basically 2 types of buildings. They're divided in series because the Soviet buildings has different series, and they have the similar design. So that's why they are in like different series. And this series level is basically more used as a practice. And another series is 317, which is basically lightweight concrete block. For this study, I have used the renovation strategy tool, which is developed by one of my supervisors for the simulation. And the inputs are coming from Estonian building registry. So, for the modeling approach, we have considered 8 renovation scenarios from non-renovated situation to fully renovated scenarios, and different single major, for example, window and roof, something like that. So for the model, we have modified the U values for renovated scenario and non-renovated scenario. So to understand the results better, we have tested the results against the non-renovated scenario to different renovation scenarios, and all the cases we have found some bold results. And for the renovation scenarios which involves window or roof, otherwise window and roof, they have moderated heating reduction to 28% maximum, while the renovation scenario which has wall involved, it has like the biggest impact as a single impact renovation scenario, and deep renovation is very clearly identifiable. In this case, deep renovation means window, wall, and roof only. So to understand the results better, we have also plotted the results against as a violin plot to see the distribution, and you can see that again the window and roof are in blue shades of the violins are in a higher demand, and wall involved results are quite satisfying. However, they are quite overlapping in this case. So to handle the results and overlaps, we have followed some tiering approach for this energy-based tiering framework. So these tirings are series specific. So the tire 1 is non-renovated, tire 2 is partially renovated, but this case we have window and roof only, not the wall. And third tire, which has the better impact, is the third partial renovated, and the fourth tire is deep renovated. So to handle the overlap, we have used basically two logic. One is common practice logic, and second is median-based boundary logic. So for common practice, in Estonia, most of the buildings has been, like almost all the buildings has been through at least the window has been changed. So in that case, if they are like overlapping between 1 and 2 tire, then we kind of understand that it is like the window is at least changed. So in that case, we put the logic tire into tire 2. So to understand the results better and to understand that if it is just because of our selected U value or not, we have also tested the results against most optimistic U values, and the pattern is very similar, just the numbers are lower. You can see still the window and roof is still in a higher value range. In the colored are the optimistic values, and gray are the realistic values. They're also compared against each other. And also the wall involved scenarios are very lower range comparatively. And we have also tested the same method in on the subtypes of this building series. So the subtypes are basically this series has some different variations. So they are inside the series. They are in small. If they have the similar geometry, they are under same subtype. So in this case, basically the geometry is exactly same or identical, and then we can see that the non-renovated situation has one deterministic value, and again the wall involved scenarios are the best results in a way, and this case also we have less bigger range. So overall that helps us conclude that this series level variation we have found is not only not the modeling artifact, rather it's a result from variation in geometry. So based on the results we have found, we are proposing a dynamic archetype mockup tool. So if the user is inserting the building series and the heating demand, then the model can the tool can tell us that where is the building in terms of renovation state, and if the building's renovation is also in a overlapping state, in that case actually you can add the evidence. However, if also the user wants to understand the understand that which type of renovation can achieve what type of heating demand, they can also play with this. So coming back to the research question, can heating demand be used as a classifier for renovation depth? Yes, but with the other findings we had, like wall is the most dominant one. However, we found that the model is transferable, but for one country we need to readjust the models. And as a future work, we are planning to extend this study for major data, because this was a simulated data-based model, and also we are opting for having some multi-source Bayesian model for adding different type of evidence node for capturing the real-time data. And thank you.